Okay, hello everyone. My name is Jiang, and I'm honored to introduce our progress made in BIPM on the continuous and multi-GNSS IPPP time link for the UTC maintenance. And this work is done with my colleague Giulio Tagliaferro. The story starts from the Coordinated Universal Time, the UTC. It is an international time standard, and currently the PPP is widely used for the time and frequency transfer to compare the clocks participating in the UTC maintenance. And currently the BIPM applied the AirCam PPP software. It is quite good, but supports just GPS only. And the advanced form of PPP, the PPAR, is not yet operationally applied in BIPM. So in this case, BIPM is in the process of evaluating new tools for the PPP and PPAR software in the UTC calculation. PIPM UTC is the international reference time scale for the global applications. It is calculated every month in the monthly batches by the International Bureau of Weights and Measures, or BIPM, and it is generated from the highly high performance ground atomic clocks operated by the time laboratories worldwide. Now we have overall 85 labs around the world, and with over 130 receivers contributing to the UTC calculation, and supported by 72 countries. For time scale maintenance, the time and frequency transfer is essential to produce the clock comparison results or the time links in the context of the time community. For the UTC, when we applied three main approaches. The first one is global GNSS-based approach, and the PPP is the most popular one because you can calculate the receiver clocks for the global stations, just use precise products. And the second one is the two-way time and frequency transfer. The dedicated equipment transmit and receive the signals simultaneously from the GEO satellites, and all of the aerial resources can be canceled out except the receiver clocks, so resulting in good performance. The third one is the optical fiber time transfer. It is the most accurate technology for the time transfer in current, but it is limited by the distance, and it is still in developing. So now only one optical fiber in Poland is routinely submitted to the BIPM. So we are very grateful to the IGS and the ACs for their efforts put on the maintenance of GNSS service. Actually, BIPM has several years of the experience in the PPAR time transfer based on the GENE software developed by CNES using the GRG final products and the daily batch. This processing relies on the final orbit, and the time latency of the orbit is not enough for the calculation of UTC. And at the same time, the maintenance of the software requires a manual validation. And moreover, the multi-day batches are more robust and easier to handle than the traditional daily batches, but require dedicated software and continuous products. So to achieve this, BIPM has selected two PPAR softwares for multi-day PPP processing. The first one is Bright PPAR, an open source software developed by the Wuhan University. The second one is Atomium, a legacy software from the time community developed by the Observatory of Belgium. As for the products, we selected three. First one is the legacy IGS rapid product, which has been applied in BIPM for a long time. The second one is the Wuhan rapid product, and the third one is the code rapid. The IGS rapid is continuous at the day boundaries, and it supports GPS only. And for the Wuhan product, supports multi-day and multi-cancellation processing for both PPAR and the PPP solution. As for the code, it also supports a multi-cancellation PPAR processing, but is not always continuous at the day boundaries. So the dedicated efforts have been made by BIPM to align the code products to make it continuous for the multi-day processing. Next, I would like to introduce the PPPAR workflow in BIPM. First, we process the PPP and the PPPAR solution every month based on 35-day batch with 2-day overlapping with adjacent months. And then we will form the time links between the PTBB and the other receivers. As you can see, sometimes there are discontinuities as indicated by the arrow, even for the multi-day IPP solution. This is caused by the integrated cycle sleep. So in the third step, we will bridge this kind of discontinuities by the integer narrow length cycle. And then we get a continuous red line. At the same time, we also care about the accuracy of time link. So we will further align the bridge the PPPAR link to the calibrated PPP link. That is the red line. Next, in this study, we will evaluate 5 new links based on prior PPPAR software for 12 months in 2028 on about 90 stations. The first one is IGS PPP solution, and then is the PPAR and the PPP solution based on Wuhan Rapid products, followed with PPP and PPP solution based on code Rapid products, but aligned by BIPM. To assess the performance of the PPPAR link, we introduced the 2 individual links. The first one is optical fiber in Poland, because the optical fiber is better than PPPAR link in accuracy, so we can use it as a benchmark. We calculate the differences between PPAR and the optical fiber, and their align division can be used to evaluate the performance of PPPAR link. Second, we have also 20 two-way links between the PTB and other labs. So even though the noise level of two-way is a bit higher than PPAR link, but the difference between PPAR and two-way can still be applied to evaluate the robustness of PPAR link. Third, we also analyze the overlapping bias for the overlapping period for each kind of a link. First, I would like to show the aligned division of PPPAR minus optical fiber. But for each kind of link, we have 12 solutions for 12 months. So you can see that the the legacy PPP link stay above the PPPAR link. And when we come into the median, it is shown that the PPPAR based on Wuhan and the code products perform better than the PPP link, especially in the long term. So specifically, PPPAR achieves the largest improvement for tau of 14 days, from 310 to the minus 16 to 1.510 to the minus 16. But when we come into the PPP link based on Wuhan and the code products, we find that the PPP link based on Wuhan products show larger deviation in the long term. So it seems like a issue between consistency issue between the clock and student observations. So we report this issue to the Wuhan team, and they have fixed it. So we are very thankful to their prompt response to our report. Oh, sorry, there is a mistake. But in this slide, I would like to show the aligned division of PPPAR minus two-way link for the 20 two-way links at the average time of 14 days. And the different lines represent the median of each two-way link. So we generally see that the PPPR link based on Wuhan code products are comparable or better than the two-way links. So the PPR solutions show the higher robustness than PPP link, even though the performance of the island division can be affected by the higher noise of the two-way itself. And finally, we analyze the mean bias for the overlapping period for each kind of link. In this figure, we just show that the PPR link based on Wuhan code and the IGS PPP link perform the approximately normal distribution, indicating that they can achieve a good consistency between different months. And when we come into the PPP link based on different products, yeah, again, the Wuhan PPP link show a bit flatter distribution corresponding to the issue we mentioned in the previous slide, while the rest of three others agree well with each other. So finally, we draw some conclusions. The PPPAR and the PPP link has been based on prior PPPAR software have been extensively tested, and the multi-constellation PPPAR outperforms the current PPP solutions in terms of stability under operational-like conditions. And in the future, we will continue the test of the PPAR solutions for the operational use in UTC. And we also encourage more ACs to provide continuous products. And we will also integrate autoimmune software into the BIPM PPAR operational-like workflow. And finally, the collaborations are welcome if you have IPP software or links would like to be compared with BIPM. Thank you very much.